Hello students, in last lecture we solved examples from exercise 3.1. Let us solve one more example from it. So the example is, does series n plus 1 upon n plus 2 n varies from 1 to infinity converge or diverge? Next example in it, does series n plus 1 upon 10 raised to 10 into n plus 2, okay, n varies from 1 to infinity, converge or diverge? So let us check one by one. Okay, so first we have to find out whether first series is converge or diverge, second series converge or diverge. So here we can use necessary condition for convergence of series. What is that? What is that statement we have seen? Series an is if series an is convergent, then limit of an as n tends to infinity is equal to 0. Okay, we have seen this statement. What is its converse part? If limit of n is not equal to 0, then series diverge. Okay, so let us check limit of n for these two series. So in solution, let us check for first series. Given series is series n plus 1 upon n plus 2, n varies from 1 to infinity. Okay, we can write it as series n varies from 1 to infinity. What is n here? Where an is equal to n plus 1 upon n plus 2. Let limit of n as n tends to infinity is equal to limit of n plus 1 upon n plus 2 as n tends to infinity. That is, limit n tends to infinity. We can take n common here. There will be what? 1 plus 1 upon n, upon taking n common 1 plus 2 upon n. Okay, n will get cancelled after taking it common. Okay, next after applying limit, what will be? It will be 1. Okay, so we get limit of n as n tends to infinity 1, which is not equal to 0. Okay, we get it not non-zero number. Therefore, by necessary condition of convergence, this given series is divergent. Therefore, by necessary condition of convergence, okay, series, which series? This series, by necessary condition of convergence, this series is divergent. Okay, now consider another series, second series. So for that, so let us take this given series is equal to series, I am giving it name as un, n varies from 1 to infinity, where un is equal to n plus 1 upon 10 raised to 10 n plus 2. Now we will check its limit. Limit of un as n tends to infinity is equal to limit n tends to infinity n plus 1 upon 10 raised to 10 n plus 2 is equal to limit n tends to infinity. Take the higher power of n common, that is, take n common. Here will be 1 plus 1 upon n. In denominator, taking n common, there will be 10 raised to 10 1 plus 2 upon n. After applying limit, what it will be? 1 plus 0 upon 10 raised to 10 into 1 plus 0. That it will be 1 upon 10 raised to 10. Okay, which is not equal to 0. Therefore, again by necessary condition, we can say that given series, this given series is divergent. Therefore, by necessary condition, given series is divergent. Okay. Now let us move towards the next topic, that is series with non-negative terms. Now what is series with non-negative terms means what? All terms will be non-negative. If all terms of the series are non-negative, then that series is series with non-negative terms. So its definition is a series an, n varies from 1 to infinity, is said to be series with non-negative terms if an greater equals 0 for all n belongs to I. Means what? For all n belongs to I, an greater equals 0 means what? Every term of the series is non-negative. It is greater equals 0 means non-negative. That is what it means. That is, if every term of the series is non-negative, then the series is called as series with non-negative terms. Okay, every term of the series is non-negative, then that series is series with non-negative terms. Now let us see the theorem related to this definition, that is series with non-negative term. So the theorem is, if series n varies from 1 to infinity, is a series of non-negative numbers with Sn is equal to a1 plus a2 plus up to an, n belongs to I, then a part is series an converges if the sequence Sn, n varies from 1 to infinity, is bounded above, and B part is series an, n varies from 1 to infinity, diverges if sequence Sn, n varies from 1 to infinity, is not bounded above. Okay, so let us prove it. What is given? Series an, n varies from 1 to infinity, is a given series. Okay, this series is given, and one more thing is given. Sn is what? Partial sum of the series with Sn, and Sn is equal to a1 plus a2 plus up to an. What we have to prove in A? If this sequence Sn is bounded above, then series convergent. If sequence Sn is not bounded above, then series divergent. Now, what is convergence of a series? We know that any series is convergent if its sequence of partial sum is convergent. In any series is divergent if its sequence of partial sum is divergent. Now, to prove A, what is given in A? What is given? If sequence is bounded above, means we will assume that sequence Sn is bounded above. Okay. Now, how the all terms of the series? It is series with non-negative terms. Okay, means here we know an is greater equal 0 for all n belongs to I. All terms of the series are greater equal 0. We know this fact. Next, we will check whether sequence Sn is increasing and decreasing. Now we assume that sequence is bounded above. Okay, Sn is bounded above. If we show that if sequence is increasing, or we may say it is if it is non-decreasing. Okay, if it is non-decreasing and bounded above, we know the theorem that if the sequence is non-decreasing means increasing and bounded above, then it is convergent. So using that, what we get? We get Sn is convergent, and therefore its series will be convergent series. So let us check whether this series Sn is increasing or what. So for that, here an greater equal 0. Okay, this is given fact that series is of non-negative terms. Now let us check. Now Sn plus 1 minus Sn. What is Sn plus 1? A1 plus A2 plus up to An plus 1. Okay, minus Sn is A1 plus A2 plus up to An. So after subtraction, what we get? An plus 1. And we know that it is always greater equal 0 from equation 1. Okay, that is what we get. Sn plus 1 minus Sn is greater equal 0. What this implies? Sn plus 1 minus Sn is greater equal 0. What this implies? Sn plus 1 is greater equal Sn. What it implies? That is next term is greater than previous. Means what? Sequence is non-decreasing. So here we get, therefore sequence Sn is what? It is non-decreasing. It is non-decreasing. And what is given? It is non-decreasing, and given that it is bounded above. Okay. Therefore, by theorem, what we get? Sequence Sn is convergent. If the sequence of partial sum of the series convergent, so definitely, therefore, series n varies from 1 to infinity, is convergent. Okay. If this sequence Sn is bounded above, then given series will be convergent series. Now to prove part B. What is B? What is given in B? So in B, what is given to us? If sequence Sn is not bounded above, sequence Sn is not bounded above. Again, series An is of all non-negative terms. Means what? And An is greater equal 0 for all n belongs to I. Now let us check again whether, now we already proved that sequence is what? In part A, we proved that sequence is non-decreasing, means increasing. We can check it once again. So now, so similar to previous part, Sn plus 1 minus Sn, that is A1 plus A2 up to An plus An plus 1 minus A1 plus A2 up to An, which is equal to An plus 1, which is greater equal 0. That is Sn plus 1 minus Sn is greater equal 0. What it get? That is sequence Sn is non-decreasing. Okay. We have seen the theorem. If the sequence is non-decreasing, means you can consider it as increasing and not bounded above, then by theorem it will be divergent. That is, here sequence Sn is non-decreasing and not bounded above. Therefore, by theorem we get sequence Sn is divergent. Therefore, series related to it, that is series n varies from 1 to infinity, is divergent. Okay. So, if the series is of non-negative terms and if the sequence Sn is bounded above, then the series An is convergent, and if the sequence Sn is not bounded above, then that series An will be divergent series. Okay. Next topic is geometric series. Now what is geometric series? Its definition is the series 1 plus x square plus x cube plus dot. That is series x raised to n varies from 0 to infinity, such type of series where x is non-negative number. Okay, the series 1 plus x square plus x cube plus dot 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 of non-negative numbers is called a geometric series. Okay, this is geometric. Such type of series is geometric series. Related to it, we will prove one theorem. That first part of it, if x is between 0 to 1, okay, then the geometric series x raised to n varies from 0 to infinity, converges to 1 upon 1 minus x. And its second part is, if x greater equal 1, then series x raised to n varies from 0 to infinity, diverges. So geometric series is converges to 1 upon 1 minus x if and only if x is between 0 to 1, and it is divergent series. Geometric series is divergent if x is greater equal 1. So let us prove it. Prove first part, that is x is between 0 to 1. Suppose x is 0.5, then this related geometric series will be converged to 1 upon 1 minus 0.5. Second, what is meaning of second? If x is any real number greater equal 1, then the related geometric series will be divergent series. So let us prove it. Let us prove the first part, that is, let us prove statement 1. Proof. First statement. Let us consider x is between 0 to 1. What is our claim? What we have to prove? That series x raised to n varies from 0 to infinity, converges to 1 upon 1 minus x. So let us prove. This is given series. So let us take its partial sum. What will be Sn? Sn is equal to partial sum of series x raised to n from 0 to infinity. Therefore Sn will be, that is 1 plus x square plus up to what? X raised to n. Total n terms. For n belongs to I, Sn will be this. Therefore Sn will be, we have the formula for this addition. What is that? 1 minus x raised to, if here is n, 1 minus x raised to n plus 1 upon 1 minus x. We can write it as this. It is of the form p upon q. We can write it again, we can separate it, we can write it as 1 upon 1 minus x raised to n plus 1 upon 1 minus x. Okay. If we apply limit on left hand side, it needed to apply limit on right hand side. Therefore limit of Sn as n tends to infinity. Here is no term of n, so this is constant, it will be as it is, minus limit n tends to infinity, x raised to n plus 1 upon 1 minus x. Now we know that what is x here? X is between 0 to 1, and we know that if x is between 0 to 1, then limit x raised to n plus 1 as n tends to infinity will be 0. So what will be this? Therefore limit of Sn as n tends to infinity, it will be 1 upon 1 minus x. What is reason? Since x is between 0 to 1, limit n tends to infinity, x raised to n plus 1, this value is 0. So what we get? Limit Sn is 1 upon 1 minus x. Means what? Sequence Sn converges to 1 upon 1 minus x. Means Sn is convergent sequence, therefore its related series will be convergent. So from this we can write sequence Sn converges to 1 upon 1 minus x. Therefore given series converges to 1 upon 1 minus x. So therefore here we will write, therefore sequence Sn n varies from 1 to infinity, converges to 1 upon 1 minus x. Therefore series x raised to n varies from 0 to infinity. So this series converges to 1 upon 1 minus x. So always remember that in geometric series 1 plus x square, if in this series x is between 0 to 1, then that series converges to 1 upon 1 minus x. Now let us prove part second, that is if x is greater or equal 1, then geometric series diverges. Second, let x greater or equal 1. Now here there are two cases, either x is equal to 1 or x greater than 1. So this is given. What is our claim? We have to prove series x raised to n diverges. So here there are two cases. Case 1. Case 1. What will be case 1? X is equal to 1. Let x is equal to 1. Then what will be Sn? Then Sn will be 1 plus x square plus x raised to n for all n belongs to I. But what is the value of x? It is 1. So it is 1 plus 1 plus 1 plus 1. How many times it is? How many times it is? N plus 1 times. Okay. Because it is n, 1 to n and this one. So it is n plus 1 times. Therefore this addition will be n plus 1. Okay. For all n belongs to I. What will be limit of Sn? Therefore limit of Sn as n tends to infinity will be limit of n plus 1 as n tends to infinity, which will be equal to infinity. What it means? Limit of sequence Sn is infinity, means sequence Sn diverges. Therefore sequence Sn is divergent sequence. Sequence Sn is divergent, therefore its related series with it is divergent, therefore series x raised to n is divergent. Okay, this is case 1. Now another case, case 2. Let x is greater than 1. So in that case Sn is same. Okay, now here, now x greater than 1, so we can write 1. This x greater than 1, x greater than, so this will be greater than, because this x greater than 1, x square will be greater than 1 square, like this, plus dot 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 plus 1. And what is it will be equal to what? N plus 1. Okay, this addition is n plus 1. That is what we get. Sn is greater than n plus 1. Okay, where this n belongs to I. Therefore, and again here, as n tends to infinity, what happen? As n tends to infinity, this n plus 1 tends to infinity. Therefore, as it tends to infinity, Sn tends to infinity. Okay, so here we can write, and n plus 1, this tends to infinity as n tends to infinity. Therefore, definitely the terms next to n plus 1 will tend to infinity. As it reaches to infinity, the next means terms greater than it definitely reaches to infinity. Okay, and n plus 1 tends to infinity as n tends to infinity. Therefore, Sn tends to infinity as n tends to infinity. That is what? Limit of Sn as n tends to infinity is equal to infinity. Therefore sequence Sn is divergent, and therefore we can write, therefore series An is divergent series. Okay, when we are seeing the case when x is greater or equal 1. So therefore here we can write, therefore series, that is x raised to n, is divergent. Okay, that is proof of theorem. Okay, let's stop here. In next lecture we will solve some examples and see one theorem. Thank you.